Hi everyone, great to meet you. I'm Catherine, and I'm going to be talking to you today about a work that came out earlier this year that I'm super excited about. I'm really delighted to get to share it with you. And so I'm the lead author on this work, but many of my coworkers at Anthropic contributed. It was a big team effort. A lot of wonderful work went into it, and I'm delighted to share it with you today. So the title of this work is In Context Learning and Induction Heads, and I will jump in and explain some of this to you. I'll also, part of this talk, I'll give a tour of the paper itself so that if you arrive at the actual paper, you'll feel a little more oriented as to where this material is coming from if you want to go back to the paper and dive in yourself. So I'm just going to set my video on the side here so that you can hopefully still see my face while I'm talking through the slides. I thought that might be a little more engaging than just looking at the slides themselves. Without further ado, let's jump into it. So the main hypothesis of this paper is that induction heads, which are a certain kind of attention head, might constitute the mechanism for the majority of all the in-context learning in large transformer models. So we'll go into more in depth into what are induction heads, what is in-context learning, and why we think they might be connected in this way. But I wanted to just start with this presentation that what we're doing with this work is making a causal, as best we can, a causal connection between a type of attention head and then a specific behavior that the models show. So just to briefly emphasize induction. We'll get into more detail soon, but induction is sort of if you've seen a pattern in the past, you expect that pattern to continue in the future. So if you saw a token A followed by token B in your sequence of tokens so far, you might expect next time you see the token A, it might be followed by token B again. So it's a way to learn in context these successive patterns using kind of an inductive rule. And the main empirical finding that we would like to present is that the development of induction heads co-occurs with this visible bump in the loss curve. You can see that as this curve goes down, there's a specific chunk that happens in the loss curve that you can see straight away. After actually quite early in training of this is a one layer versus a two layer transformer. So the two layer transformer is showing this particular feature in the loss curve. And we'll go into more detail, other things that co-occur with this sort of broad, highly visible detail in the overall behavior of the model and why we can track down this particular bump in the loss curve to the development of these types of induction heads specifically. So before I get into the experiments, let me just ask, why is this cool? I think this is cool for two reasons. One is that we know what this bump is. Many a time have I seen a bump in my loss curve when I've been training a machine learning model, and you usually don't get to know what exactly happened at that point. But in this case, we know exactly what happened for the small models. We also extrapolate to large transformer models. We know mechanistically what these heads are doing and why that's turning into a stark improvement in the loss at that particular point. I think this is very cool. It's very rare in machine learning that you get to go from a crisp mechanism to an observed behavior in this particular way. I also think induction heads are really fun because they can make completely novel associations. So these are not learned statistical associations. This induction pattern allows you to pick up new associations in the context that were not seen during pre-training and then carry those associations on into later parts of the context. So as I said, this work is on arXiv, but most primarily we have it up on a website. The reason we have it as an HTML version as the primary version is there are interactive diagrams in this work. But of course, if you'd rather look at the PDF on arXiv, that is available too. And I'm going to go through sort of the table of contents of the work as presented in the sort of web version, so that as I'm going through this talk, if you return to the paper, you'll be able to look up these sections and get more detail yourself. So we'll start with sort of these key concepts that I'll introduce that will help understand what arguments we're making for our core hypothesis. In the paper, we present six arguments for the core hypothesis. I'm going to focus most on the first through fourth argument and gloss through the other two more quickly. And then I'll quickly give a tour of the remaining sections, the model analysis table being just a large table of our findings across numerous different models running similar experiments on many models at the same time, and then moving through sort of related work and discussion of where this might be going and what we might think it means. A final thing I'll emphasize is we got some replications from colleagues at other organizations. I'm delighted that they took the time to submit these, and I'd like to make sure to highlight their fine work there too. So before I talk about attention heads, I imagine many people in this room might have worked with transformers. If it's been a while, let me just review roughly what's going on in a transformer. So the core thing that makes up the transformer architecture is this residual stream, where after your tokens are embedded, then that embedded vector representation will be added to throughout the successive series of layers, but additively. It's sort of whatever you get from the embedding state will just get elaborated on before at the end of the model you reach the unembedding state. And so I've sort of marked this as sort of the resid part of the transformer, and then each layer after the embedding goes through two different types of block, an attention type block, and then an MLP type block. I can't decide if I should be gesturing with my hands or with the cursor on the screen, since you can see both, but I think they're probably about equally good. So yes, each layer goes through an attention phase, and then the MLP, the multi-layer perceptron, it's just a regular sort of single layer neural network phase. We'll be focusing on the attention layers in this work, and particularly a component called the attention head. So I'm about to put a lot more complexity on the slide. If you've seen transformers before, this might not be too alarming. If you've never seen transformers before, this is probably too quick for you to learn on the fly, but I hope it's a refresher for anyone who has seen this before. So the two parts of the attention operation, which works somewhat independently. The first part is the figuring out where to attend. So attention will flow from the present token being considered backwards to sort of pull information from all the previous tokens in the context. And this operation is a softmax, so often it will look largely like it's sort of reading from just one previous token, but of course not always, softmax being as it is. So we call this the query and key circuit. So the source, I guess we're calling this destination. The current token is emitting a query, which then gets matched by dot products to the keys being emitted for this particular attention head by the tokens that have come before. So that's the query key circuit that's controlling where this head is attending to. And then once that attention pattern, which is then going to be a weighting over the context, once that is set, then each previous token in the context emits a value through this WV matrix, and those are weighted and transformed through the output WO matrix to change the logits, or to basically be written to the residual stream. So again, the query key circuit determines where attention is flowing, and then the output value, the OV circuit, determines what the impact on the residual stream is going to be, how it's going to change the predictions. So that's a transformer overall. We'll just go through the key concepts as used in this work as well. So the first one being in-context learning. I just grabbed this paragraph straight from the paper because I thought it was a good explanation. Basically, in modern language models, later tokens are easier to predict than earlier tokens. What's going on in the earlier part of the context is being used to better predict tokens later. And so this is often called in-context learning. It can be called meta-learning, although I personally don't favor that term, as it suggests that the model is learning something new in the context. My story is a little more like the context is helping it select a particular behavior that it might already know in some sense. Nonetheless, we, for the purposes of this work, call it in-context learning rather than meta-learning. And we we distill this down to a particular score. This is something fairly ad hoc that we came up with for the purposes of this work, although we tested that our findings are not sensitive to these particular choices of which token to use, but we're describing the in-context learning score as the loss of the 500th token in a length 512 context, minus the loss of the 50th. So this is how much it's improving over a fairly long range. And part of why we choose this token index-based definition is it's more agnostic to questions like if you talk about few shot learning from the context, then there's a notion of what's a shot and what is the task, and we want to be a little more agnostic to those choices than that framing would imply. The next concept I want to introduce are what are induction heads. I touched on this briefly. We'll go in a little more depth so that the rest of our findings will make more sense. So as I mentioned, this induction pattern is if earlier in the context the token A was followed by B, then now we see this token A again, and we might predict it'll be followed by B again. This is simple inductive reasoning. It's implemented using two different aspects of what the induction head itself is doing. That is to say, we find specific heads that are doing this operation. Through the QK, the query key circuit, they're doing that prefix matching. So if the present token is A, it'll look back to previous tokens preceded by A. And then the effect it has is to copy the tokens it attends to. So we're currently on A. Last time A was followed by B. So we'll attend to B and copy it. That's the induction head operation. So yes, prefix matching and copying together form the induction head behavior, each through a different part of the attention head circuit. I want to emphasize that the induction pattern is not picking up statistical associations. It works on completely random tokens. So here's an example from the paper where I've generated truly random token indices, category, 40, IDs. Note, this is nonsense. It's never seen these associations during pre-training. Nonetheless, if you repeat this pattern in the context, it will learn that last time we saw this token node, which is quite an arbitrary token, it was followed by this other fragment struction, and even though this is not a statistical association from the pre-training text, it has learned the induction pattern at a more general level, and so it knows to attend to the token followed by that followed this token last time, so it can copy it and make it more likely again this time. I think this is really cool. I think induction heads are super cool. I love that they are demonstrably allowing models to learn associations they never saw during pre-training because the basic induction pattern did hold during pre-training and they're able to learn that. So I think this is fantastic. I'm going to skip this third key concept. I think it's not as crucial for the things I want to cover in this particular talk, but please check it out if you go to the paper. So moving on to the arguments we make. And again, let's revisit what is this hypothesis? What connection are we trying to make? We are trying to connect that induction heads may be the primary mechanism for the majority of in-context learning for transformer models in general. This is a bold claim. I will note we do think may provide is approximately the right strength of conclusion from the evidence we have. We'll be as careful as we can to clarify where we have more like conclusive evidence, where we have more like suggestive evidence. I can see some ways that this hypothesis might end up being false, but we've collected some evidence that points in this direction, and we think it is a interesting hypothesis that I would love to see future work track down in more depth. So going briefly, what strength of evidence we have for this claim. So we've studied these three different categories of models. We've studied small models with no MLP layers, which reduces the complexity and allows us to do sort of more mathematically crisp work. By small, I mean 1 through 6 layer transformers. These are quite approachable models to work with. We also study small models with MLPs, where the argument that the induction heads contribute the majority of in-context learning becomes something we cannot state with as much confidence, but we still have a decent amount of evidence for. Then to extrapolate to large models, we no longer have the causal evidence that we got from the ablation studies I'll describe later on the small models, but we do still have correlational and mechanistic evidence that induction heads provide at least some of the in-context learning, and then correlational evidence that it's still the majority, although I think the further up you get, the further away we are from the base of where our argument is strongest. So I'll run us through the arguments, and then I'll see how much time we have to sort of go in more depth into each of them and do a tour of the paper. So the first argument is macroscopic co-occurrence. That's what I showed before and called the phase change, or this bump in the loss curve. So this is where the transformers undergo this bump early in training at the exact same time as when induction heads form, at the exact same time as when in-context learning dramatically improves. All these things happen right on top of each other. It's in fact one of the most obvious shifts. It turns up in kind of a PCA of what the model's behavior is. So this large shift in behavior that's visible on the training curve is also when induction heads form, so these things co-occur macroscopically. We also have a perturbation argument where we change the transformer architecture in a way that shifts whether and when induction heads can form. And as we do this causal perturbation of the architecture, we also see that the in-context learning improvement shifts precisely to match. So we are perturbing induction heads, and we are getting a corresponding adjustment in in-context learning. Another piece of more causal evidence that we have is this direct ablation type of study. So we knock out induction heads at test time in the small models and see that in-context learning gets substantially worse when we remove induction heads. I will say this work took a whole bunch of GPUs. I was running this on our sort of spare single GPUs for quite a while and using up a lot of spare capacity on this work. So even though these models are small, I ran hundreds and thousands of ablations to try and bring this evidence to you. So I am delighted that others can benefit from that. Finally, the fourth argument I'll spend time on today is finding specific examples of generality. So, I mean, induction head generality. I'll just sort of walk through this. So we define induction heads very narrowly, that they copy literal sequences. Last time I saw A, it was followed by B, so it's followed by B again this time. That will just get you very like verbatim copying behavior. And just blatantly, it is not at all plausible that verbatim copying is the majority of in-context learning. That's not consistent with how powerful transformers seem to be. However, if we look at heads that are selected because they do literal copying, these same heads also do other sophisticated types of in-context learning behavior, including highly abstract behavior. So this is where it becomes plausible that these same heads that do the literal induction behavior also explain a large fraction of in-context learning. And I've put, again, this little sort of simple guide where last time we saw something like A, we said something like B. So now we're seeing A, let's say B. So this asterisk, or this sort of fuzzier induction pattern, lends plausibility to the notion that induction heads could be backing the majority of in-context learning. So that's a quick tour of the arguments. So at this point, I'm going to dive into the paper itself and sort of drop out of the slides and give you a tour of some of the figures sort of as they are in context in our HTML paper, and also quickly show you one of the interactive diagrams that I think is most helpful. So let me pull this up. As I said, this is at transformercircuits.pub. I would love for you to check it out. I also get another chance to credit all my fantastic co-authors, including sort of the middle section of this is largely folks who worked on our training infrastructure, our models, which allowed me to do this work. Let me just expand this a little more so that table of contents pops up. Sorry, I have to hide my face. Goodbye for now. I'll be back. So as we march through these different, the key concepts and the different arguments, I'm just going to dive us into argument 1, where this is the phase change. So this is that macroscopic co-occurrence. One thing, so let me just point, I'll start with the 2-layer model, and then I'll explain sort of what the 1-layer model is doing here. So in this 2-layer model, we are showing this in-context learning score. Again, that's the difference between the 500th and the 50th token in terms of loss. The x-axis here is training time. So near the beginning of training time, there's only a small improvement. I guess, this is negative, right? Lower loss is better. So there's a small improvement from the 50th to the 500th token. And then over the course of this section we've highlighted in yellow, this part in training, during that part, the loss improves, the in-context learning improves dramatically and stays that way. And we see this in any 2-layer and above transformer that we've studied has this behavior. Now you'll note it doesn't show up at all in the 1-layer transformer. And the reason why is a detail about induction heads. 1-layer transformers cannot form induction heads. I'm going to gloss over that in just a few sentences. I recommend you check out this paper or our previous paper for more on why. But briefly in a few sentences, it's because the not the copying behavior, but the prefix matching behavior needs information about the prior token to the attended token. And so that information has to get moved in an earlier layer. And if there's only 1 layer, there's not enough time for that information to get moved. So 1-layer transformers cannot form induction heads unless we make other architectural changes, and so they do not have this bump. So this is showing simply where that in-context learning improvement suddenly shows up. And this co-occurs with where induction heads form. So here on the y-axis, I have a simple score. It's a heuristic score that I made up in collaboration with Chris that ranks how much the prefix matching behavior is what this head is doing. And you can see the 1-layer model never forms heads that are doing prefix matching, and the 2 and 3 and above layer transformers abruptly form heads that are doing prefix matching at exactly the same time as the in-context learning improvement was showing up. So this is what we call the phase change, and as advertised, it also shows up as a bump on the loss curve. Again, everything except the 1-layer. I found it really fun after working on this project to go look at open source models in the wild or other people's loss curves that they post on Twitter. And if you look in this early-ish regime, you can see an induction bump on basically every transformer loss curve out there in the wild. So I feel a little like a bird watcher, like an induction bump watcher permanently now after doing this work. So this is that loss bump where the 2-layer and above transformers have this sudden improvement that the 1-layer transformer never has. I mentioned we also did kind of a PCA analysis. I'm going to skip over this, but I think the very quick summary is that this induction head is one of the main things going on. You can see it in the first and second principal components of the sort of behavior of the model. One thing I find very cool is that you can look at a point before and after the phase change. And again, I didn't explain this graph on the left. We'll just zoom in on the right. We now have the difference in loss, or sort of token predictions, from before minus after the phase change. And so places where there are repeated text is where the model better predicts tokens after the phase change. So this is just empirical. I've just done sort of a difference between these two snapshots. But nonetheless, it's these repeated chunks. Dursley's is repeated. This is the opening paragraph of Harry Potter. And then the cases where it got worse are where the same token it's seen before is followed by something different. So induction heads would be quite surprised by this, and those are exactly the cases where probability gets worse after the phase change. So moving on, the second argument, as I mentioned, was a interventional argument. So we basically changed the transformer architecture in a way that shifts the formation of induction heads. How long do I want to spend on this? I guess I'll say what this architecture does. So these are the regular models up top. These are this smeared key architecture tweak below, which allows the one-layer model to form induction heads when it couldn't before. The way it does that is with this parameter that interpolates between the key for the current and previous token. So it means that you can attend to B using the key from A, which preceded you, without needing an earlier layer to do that movement for you. So this, this new architecture, it's not necessarily gonna win any prizes or state of the art in any sense, but it's good for this particular experiment where it means induction heads can form straight away, and they don't need two layers to do so. And so again, the reason that we like this experiment is that we can sort of move this co-occurrence where we're seeing again the in-context learning score, and then where the induction heads form, and the induction heads move along with this in-context learning score, sort of in lockstep when we perturb the architecture. Finally, I guess not finally, second to last, we do this knockout experiment, this ablation experiment. So I'll just drop in again to the diagram that's sort of the core diagram here. So what we're showing here is each individual head in the second layer and what its effect is on the score. So you can see that if you knock out the induction heads, the in-context learning score gets worse, up is worse, and so they've been colored by how induction-like that head is at that particular point in training. Again, training tokens is on the x-axis. And all of these heads that have a substantial worsening when removed are induction heads. So this is another piece of causal evidence that removing the induction heads specifically has an effect of worsening that in-context learning behavior. So this final one, which is sort of the main reason why we like having HTML papers, is we get these dynamic visualizations. So this argument is that even though we've defined induction heads as being the ones that can copy truly random sequences and copy them verbatim, they can also do other cool things. So I'll just show you how this visualization works. So if you hover over this repeated paragraph, you can see where the attention and where the logits are flowing. So here, the last syllable of privet drive, you can see that the attention and the logits are sort of flowing to the last place that we saw this before. So it's attending to drive so that it can increase the probability of seeing drive again, and then this logit attribution is saying like, to what do we attribute that having happened? So it's sort of this combination of last time we saw A, we said B, and so this time we're seeing A again, and so we predict to say B again. So again, this is just the literal induction pattern. Now let's get to cool stuff. So here's another interesting behavior that transformers can do is translate between languages. So this head does translation between English, French, and German, and it is also an induction head. So we're not showing it do literal verbatim copying of random sequences, but it can do that too. So here we can see it's doing sort of the same induction-like pattern across languages. So in French, this would be, this is the largest temple that I've seen, although of course in French, and it attends back to the last place it saw that semantically, even though the, I guess in this case, temple is the same. I should show you a better example. That I've seen, yeah, so that is still matching, even though the language is different. Ever seen, seen is matching. So even though the literal token is not matching, the semantic matching is enough to get this head to use this induction pattern. And then here we have a very contrived pattern matching. It's the type of thing you might think a few-shot prompt would be able to elicit from a typical model. So we have sort of months followed by either animal or fruit or colors. And then we just have these sort of 4 categories. And so we vary which month, animal, fruit, color, and we see if it can still sort of produce this category, this categorization. So very classic, few-shot, in-context learning. And to just pull out a particular example, January bird, so that's month animal. The colon is sort of pulling predictions from the last time that it saw month animal, even though none of these really match. And in fact, even though gray bird would technically match, it's managing to ignore that. So I think this is a very cool example where, again, this head also does literal copying of truly random sequences, but in addition to that basic induction behavior by which we selected it, it is additionally showing a more complex behavior as well. So for the purposes of this paper, we present just this anecdotal evidence and also sort of mechanistic reasoning as to why we think these heads could plausibly be responsible for more complex behaviors, but I would love to see more work on this, especially sort of empirical, kind of this kind of naturalist work where you wade through the different heads out there and explore their behaviors. I would love to see more examples being pulled out there. So just to close out this tour of the paper so that if you return to the paper on your own time, you'll be a little more oriented, through argument 5 and 6, we make some mechanistic arguments for why we find this plausible, and we also explain sort of why we think it's reasonable to extrapolate from small to large models. We also have this extensive model analysis table where we show the small models with and without MLPs. We show these full-scale models, and we show these the smeared key models, and we also show a different data set. So I'll just quickly tour through. The small attention-only transformers have this pattern consistently. The small MLPs, same pattern. We show more different ablation results of the intention heads to really drive this home. The full-scale transformers, so this is what's allowing us to extrapolate from those toy-sized transformers to up to a 40-layer transformer, also show very distinctly this specific pattern. We do ablations on these too, which also follow. Here's those smeared keys as well, and we also show a different data set than the one we usually use. The specific shape does change with the data set, but that distinct drop is unchanged. So overall, as I said, there's sort of then some final matter in the paper that I recommend checking out, including some interesting unexplained curiosities. And again, I'll skip over discussion for a sec, related work. I'll skip for a second, because I just want to highlight the work of our colleagues who replicated this before we published it, which we're very grateful for. So Adam Shirless at Redwood describes the findings of their replication, and also Tom Lieberman, who was a master's student at the time this came out, described his replication as well. All right, I'm back. So let's just wrap this up. I think we're close to at time. So just to go over again what we've gone through. So the hypothesis that we've looked at some evidence for is that these induction heads, which are doing this induction pattern and generalizing it in context to unseen statistical associations, or unseen associations rather, that were not statistically associated during pre-training, that these attention heads might be the mechanism for the majority of in-context learning in transformer models. This bump in the loss curve and other associated sort of large shifts were sort of our main empirical finding towards this. And again, why do I think this is so great? I think it's wonderful that we can find this bump, figure out exactly what it's due to mechanistically, and that induction heads are doing such cool behavior, and that we know mechanistically how they're doing that. I also quickly want to just highlight, some future safety implications. Again, I think this pertains less to models that we have today, but as we're seeing, the pace of improvement of transformer-based models is quite rapid. And so two things we might want to keep in mind. One is phase changes. So if neural network behavior changes somewhat discontinuously over training or as you scale up, it would be nice for us to know more about how phase changes tend to show up in neural networks, so that we can have a little heads up if we are about to see a sort of unanticipated algorithm or behavior, so that we can be prepared for it and characterize it as it's coming down the pipeline. The other thing to keep in mind, safety-wise, is in-context learning means that behavior could change substantially from training to deployment, right? The model behavior can sort of change during inference without further training. Like I said, the fact that induction heads are this little window, tiny window into the possibility that associations that were not present in the pre-training data set could be learned from the context. It's interesting. It sort of raises possibilities that the behaviors that you see when you deploy a model or run it on new contexts could be surprising. And so I think in some sense we all knew that, but I think it's good to have empirical evidence highlighting that possibility as well. I will wrap up here. Thank you so much for taking the time to listen. As I said, I'm very jazzed about this work. I'm very grateful to all of my colleagues, and I encourage you to check out the website, or as I said, if you prefer, the archive version where you can't hover, sadly, as HTML allows you to. Thanks so much for listening. It's been a joy.